Hello and welcome everybody to this technical walkthrough that is associated with the master thesis Electric Vehicle Range Prediction with Deep Learning. This video is separated into 3 sections. There will be timestamps on the screen, so if you're only interested in a specific part, please feel free to skip ahead. First, I will give an introduction to the general problem of electric vehicle range prediction. We will take a look at the setup and the problem we are trying to solve, and the general framework in which all further presented code will operate. Second, we will give a high-level overview over the Python and PyTorch code that was mainly used to implement all considered models in the master thesis. We will take a look at the data flow from data gathering, pre-processing, over to training and evaluation, and you will get a high-level understanding what happens in which part of the code. Third, we will look at Monte-Ana models that are also used to model the different models that are considered in the master thesis. They mirror the PyTorch implementation, though not every model is fully supported. We will take a look at each model and shortly discuss which parts are already supported or fully supported and which parts are not yet supported. First, let us revisit the task we tackled in the master thesis. Electric vehicle range prediction is a complicated subject in practice because there are a lot of factors that influence the range of an electric vehicle. Rated ranges are rarely reached and are usually only available in optimal conditions. A dynamic range prediction is necessary to let the drivers know what range they can expect from their vehicle to schedule charging stops accordingly. It is also difficult to assess how good range prediction is. There is no gold standard, since it highly depends on driver behavior. We chose a user-centric error metric, which in our case is the consistency error. Here, the range estimation is judged by the consistency with an actual ride. If a ride, for example, is 35 kilometers long, and the range prediction before says you have a range of 200 kilometers, and afterwards it says you have a range of 150 kilometers, then the consistency error would be 15 kilometers. We generalize this in this formula on screen. This allows for unsupervised training on an electric vehicle rides dataset. While we do not use the consistency error directly for unsupervised training, the concept is very close. We train on ride length prediction, and this is a quite close concept to the consistency error. We then later on use the consistency error for further evaluation, though this is not part of this video. The main data source for all our work was the EgoLife vehicle dataset. It consists of telemetry data from EgoLife electric vehicles, and vehicle status data are sampled in 1-minute intervals in this dataset. Each data point includes comprehensive information about the vehicle status, including, but not limited to, state of charge, auxiliary power use, driving mode, or minor information like, for example, windshield wiper level warnings. We post-process the data into ride data packages. Here we are able to view the data on a per-ride basis and use ride information for further analysis. There are a few data imbalances, in particular short rides are very much overrepresented in the dataset. Also, the data was gathered during the summer months, so there might be some bias here. Now, let us continue with taking a look at the PyTorch implementation of the models that we considered in our thesis. If you want to start working with the PyTorch or Python implementation, please check out the Vehicle Data Exploration folder located in 03 workspace. This folder contains another repository that I used for working on my Python and PyTorch implementations. First, please note that there is a README available with some general information about how to set up everything on your machine. Also, I've documented my virtual machine setup mostly in this vmmd file. So if you want to also run the code on a virtual machine on the Google Cloud, please check out this document. Before we go into the actual PyTorch implementations and Python code, I would like to show you the utils folder, which contains small files that are useful for working with PyTorch and also some data visualization. First, if you use a graphics card, please check out the torch GPU test.ipynb. With this file, you can quickly test if your GPU is recognized by your current PyTorch instance. With the visualize data file, you can visualize your source data. Please note that this is specific for the Ego Live vehicle data, so if you want to choose to connect another data source, you might have to apply some changes. It contains data cleaning, write analysis, charge analysis, all sorts of analyses about SOC, usage patterns, and other statistics about vehicle usage. It is quite comprehensive, so there will also be a lot of analysis that did not find its way into the final thesis. Next, there is a credentials template, which is a template file which you can basically copy and fill in your own credentials to use for the data loader that we will present later. Please note that you have to rename this file from credentials template to just credentials and move it into the root folder. We also have an ML demo file, which is not actually that much associated with the thesis. It was just a machine learning demo from scratch for some colleagues of mine. Now that we have discussed the contents of the utils folder, let's continue with the actual data processing pipeline. This pipeline starts with the data loader file. The data loader reads a set of credentials that you have to provide beforehand and downloads a set of source data or a base data set from a Postgres database and stores it into a pickle file. This is basically used for caching, so you do not have to perform the data fetching every time, as this may take quite a lot of time depending on the amount of data. After you've downloaded your data, we can continue with the generate dataset file. The generate datasets file imports the pickle file you've just created with the data loader and pre-processes it and splits it up into multiple datasets. You can perform filtering based on timing, and you can get a general idea of the data with the described method. It also cleans the data. In this case, it excludes a few test vehicles and limits the vehicles that are considered to a certain model. Here we also anonymize data, and we split up the data into test, train, and validation sets. We also transform timestamps to be easier to deal with during machine learning. Then all the created datasets are exported to CSV files. The iTrums dataset is the base dataset, which just contains the raw data obtained from the vehicles. We have a drive recognition routine that splits up the data into drives and collects statistics about them. Based on this, we also are able to generate the so-called write-trums dataset. This is a combination of a writes dataset with the iTrums dataset. Here, each data point is viewed as the start of the write and basically enriched with a final data point from the end of the write. This way, each data point also contains information about the write it is part of. Then, the write-trums dataset is also exported to CSV files. Please note that it is not recommended to commit any data to Git repositories, and these data files are also therefore entered into the git ignore file at the root level. If you are working on a virtual machine, we recommend to use SCP to transfer these files to the virtual machine instead of using the repository. Now you can start training on the data. There are two ways to train that we provide in our Git repository. There is the train Python file, and there's also the train interactive Python file, which is just a notebook. You may want to start out with the interactive Python file, as it makes it easier to debug and use or reuse intermediate results. They are quite similar, though not identical, and the train Python file is more useful for longer sustained training sessions that are not interactive. In our training file, we first try to limit randomness to improve reproducibility. We set the device to the GPU if available, else you have to resort to the CPU. We define a test schedule, a train schedule, save and load functions for checkpoints, and later on we integrate all of those functions into training cycle, which imports the data, defines loaders, and then performs training until there is no improvement for a number of epochs that we set in the epochs stopgap. Here we also define an unsupervised loss function that we got from this GitHub gist. This is used for pre-training later on. Then we set up a bunch of training experiments where you can basically just use the training cycle, and if you are just repeating the training, skip down right to this part and start it. The reason why we do not use this for extended training sessions, that depending on the setup, there might be some implementation specific issues with reconnecting to kernels that have been disconnected due to the local machine sleeping. Because of this, you will see that we set up most of our experiments here. However, the actual results were obtained by us with the train.py file. The train.py file follows the same basic principle and has identical sets of code for the most part. It is partially simplified because we do not need any visualization, but works with the same principles and the same code for the most part. Down below, you can use the train models file to set up which configurations you want to have trained. Each configuration is basically a dictionary where you can set up the parameters. Most are commented out because we did not perform all trainings at the same time, but instead split it up into different training grounds. Finally, there's a loop that iterates through the configurations and starts the training for each configuration. If you wish to perform hyperparameter search, please take a look at the param search file. It works similarly to the training file, but instead of just training a single configuration of a network, it can train a network with multiple sets of hyperparameters that you can specify. Each hyperparameter is trained separately, and then the optimal result is kept for all future hyperparameters that have to be optimized. You can set the parameter space here and basically set it in form of a dictionary where you can decide which sets of values for each parameter are considered. You can also choose model-specific parameters as long as the models can accept these parameters as a parameter in their function call. For example, here you see specific parameters that we used to optimize transformer models. After you are done training, you can take a look at the benchmark file. Here you can import different model configurations and perform a range prediction benchmark with all of them simultaneously. First, the different networks are imported and graphs for their training behaviors are plotted. and then the validation data is imported from the CSV. We set up the models for using them for inferences for the range prediction. Then we define how a range prediction looks. Here we basically have to format the validation data again in accordance to the format that we trained on to make sure that the right columns are matched here. This means we essentially follow the same pre-processing steps. However, we do this on the fly for incoming data instead of transforming the entire data set. We also set up a range prediction heuristic that corresponds to the heuristic that we described in the thesis. To prepare the data, we also have to perform padding. This does not happen on the fly and happens one time beforehand. Afterwards, we perform a right detection that also calculates range prediction errors. Here, the range prediction error for each considered model is calculated so that we can receive results from our benchmark for all models in one pass. Afterwards, we can take a look at the performance summary, which summarizes the range prediction performance of the different models considered in this benchmark. Now, after taking a look at the top-level files, let's take a look at the folders and discuss their purpose. The weights folder contains the set of all weights and checkpoints that we accumulate during our training processes. So the various train scripts will all put the weights of the models that they train into this folder. The results folder is just used by us to save figures and other artifacts associated with our results in here. The logs folder works similar to the weights folder, but instead of weights, each training cycle puts its log, but also CSV files containing the loss in each epoch into this folder. This can be useful for debugging, but also for keeping track about past training cycles. Finally, we have the model folder. This folder contains the actual models that we used for our thesis and that can be used for our train script. If you want to add additional models, this is the place to do it. We have the CNN py file, which contains our reference convolutional neural network models, the MLP py file, which contains our reference perceptron models, the TabNet py file, which includes TabNet. Please note that a lot of this code is based on the DreamQuark AI TabNet implementation. However, our TabNet version is slightly modified to fit to our framework and also simplified in some parts, as we do not need the encoder or some other parts that are included in the DreamQuark AI TabNet implementation. Finally, we have the transformers py file. This includes all transformer models excluding TabNet, which has its own file. We based our code for the transformer implementation on the annotated transformer from Harvard. However, we applied some modifications and simplifications as we only considered the encoder part of the transformer in our code. Please note that the prefix pre signifies a pre-training model that is used to generate weights for then using them as a starting point for transformer configurations. This concludes the second section of the technical walkthrough, looking at the PyTorch implementations and the Python code. Now let us jump to the Montiana models. You can find the Montiana models under 03 Workspace Range Prediction. Here, each model has its own folder, and each folder contains some dummy data, configuration files, the models themselves in the emadl file with the same name as the model, and also a connector component that is a wrapper for the model and can be used to override generic parameters of the model. There are multiple classes of models that we will look at as a whole, and in this case this would be the CNN, different MLPs, TabNet, PassFormer, and also a small test model that I will introduce later. First, let's start by looking at the MLPs. So those are the MLPL, MLPS, MLPXS, and MLPXXS. those are all multi-layer perceptrons that basically only are differentiated by their size. So let's look at the MLP-L. This model is fully supported, and all other multi-layer perceptrons are fully supported as well. This includes the CI pipeline and also their semantic support, including all of the functions used. Those are quite basic models, so this is also a baseline we use for judging how well other models perform, and also you can use these models easily to test if your Monty-Anna instance works properly. Let's look at another multi-layer perceptron model as an example. For example, the MLP-XS, as you can see, looks quite similar to the MLP-L and is only different in number of layers and size of the layers. This also applies to the other MLP models, so we will not look into them separately. We also have a CNN model, in this case CNNM. Please note that we try to call this model CNN, however, this is recognized as a keyword by Monty-Anna, and thus we call the model CNNM just to avoid this conflict. This model is also fully compiling locally, however, there are still some issues with the CI. In particular, it is unclear if the dimension handling of the convolution keyword works properly in the CI. Other than that, this model is also fully supported. We also constructed a small demo. This is called the nested stream demo. Here we wanted to try out the handling of multiple data streams in Monty-Anna. So what this experiment is supposed to test is if there are multiple data streams, is it possible to access a data stream that was created at an earlier step, or are they just replaced by new data streams? So in particular, here, this third data stream at the index position 2 is handed over with the other data streams to the second to the second block. However, in the second block, there are only 2 data streams that are used and then handed over to the get, which then tries to access the second block. As we found out, this does not work, so nested data streams or nested data stream indexing is not supported in Monty-Anna yet. We also created a transformer model. This is the first model where not everything is fully supported. Please note that there's also parameter initialization that has to happen outside of this model that is still part of the original transformer implementation. In particular, dot product self-attention over here and the position encoding over there are partially implemented in Monty-Anna, so there are predefined components that exist that are supposed to do this. However, they are not fully documented, and also there are issues when compiling this model. The same is also true for the pass-former model. This is the modified transformer model with the pass-through of the end SOC up until the last neuron, which you can see below, right here. However, this is basically including the transformer model as a subtask and thus also inherits all the problems and issues of the transformer model. So here the same thing applies with regards to the position encoding and the self-attention block. Finally, we also tried to create TAPNet with Monty-Anna. When implementing TAPNet, we ran into the biggest issues, as TAPNet requires a quite complex information flow, and this becomes quite clunky with Monty-Anna. Also, TAPNet requires certain modeling features that Monty-Anna does not support as of yet during time of recording. One of those is a dynamic handling of multiple input streams. So in particular, TAPNet includes the so-called ghost batch norm. Here, the batch norm has to be applied to multiple parts of the input data. However, it is not known how many of those data streams will be created because this depends on the input dimension. Currently, Monty-Anna has a way of dealing with multiple data streams. However, it doesn't have a way of dealing with generic data streams. So what we use as a stand-in for this functionality are those open brackets, which are supposed to act as a sort of default handling of a data stream that is not accessed by index yet. Another feature that is important for implementing TAPNet that is not supported by Monty-Anna yet are shared weights. TAPNet requires multiple shared gated linear unit layers. However, Montiana is not able to support multiple layers that share weights. To model this, we propose adding a weight ID as an optional parameter to each layer. With a weight ID, you can group layers of similar architecture into a certain group. In this case, the GLU layer would share the weight ID across multiple instances, and layers that share architecture and weight ID also share their weights. This would be a way to implement reusing the same weights across multiple points within the same network. This concludes the third and final section of this technical walkthrough. I hope that this technical walkthrough was helpful for you, and I wish you a lot of success in continuing this work. Bye.